We're back with another quantum mechanics problem. Check chapter 40, specifically problem 17. Here it is on the screen. A quantum particle is described by the wave function. Psi is a cosine 2 pi x divided by L for the interval negative L over 4 and L over 4, that little interval, x is between there, and the wave function is 0 else. A, determine the normalization constant, capital A. B, what is the probability that the particle will be found between x equals 0 and x equals L over 8 if its position is measured? Okay, so I've taken the liberty here to draw out what's important. Take a look at this. We got the wave function here. It is giving us this for this specific interval, and the wave function is 0 elsewhere. And we got our problems here, which is what we have to solve. So I'm going to start off with drawing a picture over here. It's always good to start off with a picture. Psi of x. Over here we got x. Actually, hold up. Since this wave function is symmetric about the origin over here, this is 0, I need to draw it like this. So, okay. We get the region L over 4, negative L over 4, and L over 4. So normally, how a cosine function looks is it starts over here at the top, and it goes down, and then just oscillates like that. And it's also the same on this negative side. This normally is 1, but right now the height is a, because we multiply the cosine by a, right? So this function here is psi of x equals a cosine 2 pi x over L. Right, this x over L, 2 pi x over L inside kind of stretches and squishes the function, but right now it doesn't matter. But what I am interested in is actually finding out where psi of negative L over 4 is. Right, and how I do that is I just do a cosine 2 pi. Inside x, I can now multiply by negative L over 4. Over here we have L. Okay, so how does this look? It looks like we have a cancellation of the L's over here, and we have a cancellation 2, cancellation 1. So what we get is a cosine of, we got negative pi over 2. Interesting. And if you plug in pi over 2 in your cosine, and you make sure your calculator is in radians, I think what you get is this point right over here, right? This point here is 0. This point right here is pi over 2. This point right here is pi. And this point over here is 2 pi. Wait a second. Am I tripping? No, I am tripping. This point over here is 2 pi, right? Wait a second. Yeah, because it repeats over 2 pi. And, man, hold on, I'm tripping out over here. So cosine of 0 is equal to 1. Cosine of 2 pi is equal to 1. Right between that is pi. Nice, I think that makes sense. And this is 3 pi over 2, 75% of pi. This is pi over 2. Is that true? I think that's true. Yeah. So anywho, right here we also got negative pi over 2. So what all of that told us is that you plug in negative pi over 2 inside your cosine, you get 0. And this is the same thing for L over 4, which is the second kind of boundary over here. I just plug in these boundaries over here into my x variable, right? Because x is between these bounds over here. And I determine that the height of the wave function there is 0. So I can kind of figure out that the bounds that we're looking for, these bounds over here, are the negative L over 4 and the L over 4. Yeah. And how I did this is just because I'm kind of used to using cosine. I know a bit of its parameters. So yeah, practice a bit with cosine, check a graph of cosine, see if you can figure that out. And interesting. So what that's telling us is that the wave function between these bounds is this, right? So this is over here. And we know that from what this told us here, the piecewise kind of wave function is this cosine between these bounds over here. And it is 0 everywhere else. So wherever I drew this, outside those bounds, the wave function is 0. So I'm going to just draw it like this. Boom, like this. All right, so now I'm going to redraw everything so it looks a bit more clean. I have here psi of x. I have here the x-axis. Let's draw this in green again. So we got kind of a one loop of a cosine. Actually, I drew this kind of incorrectly. It should be like that, with the maximum over here being a. And then over here we have 0 everywhere else. So this is what our wave function looks like. Equals a cosine 2 pi x over L. And again, these regions over here are L over 4 and L over 4. Cool. So what do we have to determine? Well, we have to find for part A, what is this constant equal to in front of the wave function? Like I said in the previous video, check this out. The way we determine A is we use the normalization condition, which is saying that the absolute value of the of the wave function squared is equal to 1 if you integrate over the entire bounds, negative infinity to positive infinity. Cool, so what we could do is break apart our integral so that it kind of takes into consideration our regions here, right? Take a look at these regions. We have this first region, which goes from negative infinity all the way to L over 4, negative, by the way, there's a negative sign over here. We got this second region right here, which is from negative L over 4 to L over 4. And we have this third region over here, which is from L over 4 all the way to positive infinity. So we can break apart our integral, which goes from negative infinity right here all the way to positive infinity. And we can kind of consider all these three regions. So this is allowed in calculus. All we have to do is write the integral properly here, L over 4. Now take a look at this. The integral in this region is 0. So I could literally just plug in 0 dx. Now I add to this L over 4, L over 4 here. In here, the wave function is not 0. It is actually a cosine. So I have absolute value a cosine 2 pi x over L, absolute value squared dx. I add to this my final region, which is L over 4 to positive infinity, and this is also 0. So take a look at this. I have region 1 over here. The wave function is 0. That is taken into account in this integral over here. Okay? The second region, which is the wave function here, which is actually a part of this cosine function, that is region number 2. Where that is located is right over here. And the wave function there is not 0. So you could see it here and you could see the bounds over here. So keep in mind the bounds are important. And then the third region, which is over here, which goes from L over 4 all the way to infinity, the wave function is 0. So you could see that written over here. Here we got a 0. Here we got the entire integral from the specific bounds. So this entire integral here goes to 0. This entire integral here goes to 0 because remember, an integral is an area under the curve. If the curve here has 0 height, the area underneath is 0. But this area here is non-zero. So when we take the absolute value of that function and square it, we should get a non-zero area for this second region over here. Make sense? Okay, so I'm going to rewrite the entire normalization condition. Remember that this entire integral used to be this entire integral, and all of that equals 1. So I could start off with 1 over here equals, and then I have my the integral that's left over, which is from these bounds, negative 4 to 4. I can now distribute the square, so we have a squared cosine squared of 2 pi x over L dx. If you distribute the square on a trigonometric function, you could write it over here, or you could do this and write it over here. So both of those work. I'll just keep it as this right now. And the absolute value brackets disappear because we're squaring, so everything in here should be positive. Nice. Now we have to solve this integral. So how do we do that? We have a constant over here, which is a squared, which we pull out of the integral. So let me actually write this in blue since we're solving the integral right now. Okay, now the question is, all of this equals 1. What we have to find is the answer to this integral. Now, if you haven't taken a calculus class, most of the time this integral will be generally given to you, and they'll say like this integral equals some number in the back of the equation sheet. But if you don't know how to solve it and you're expected to solve it on a test, I'll give you a trick here. So the first trick is simplify the integral using u substitution. So here I have a complicated thing inside the cosine. So I'm going to say this is u. So if I u sub, I do u is equal to 2 pi x over L. Here I have a dx, and I also want to determine du. So how do I determine du? I just take a derivative of this side and the other side. The other side we get 2 pi over L, and the x becomes a dx. Now if I divide everything on the other side, I have du times L over 2 pi. I'm just using some algebra here to simplify. Dx. So I can use this to replace this, and I can use this to replace this. Now my integral becomes a bit more simple. I'm going to go back to the black ink here. I have a squared integral, and inside the integral what we have is cosine u, and then this dx was L over L over 2 pi du. Now, what's important is these bounds here are actually x1 is equal to and x2 is equal to. Now, since we've changed to u, we actually have to change these bounds again. So we have u1 is equal to 2 pi times x1, which is L over 4 over L. So we could see actually the L cancels here, this 2 cancels with this 4, and it becomes 1 over 2. So what we get is pi, wait a second, over 2. I guess we could do the same thing for u2, which is 2 pi times negative L over 4 over L, which equals to negative pi over 2. And by the way, this whole u here is squared. I forgot about that. So we have negative pi over 2 here, pi over 2 here. This is a constant, so we can move it out over here, which gives us a squared L over 2 pi integral pi on 2 negative pi on 2 cosine u squared du. Now, if you don't know how to solve this integral, like I said before, normally they should give you this integral equals this, but I'm going to take a look. I actually did this problem before and I kind of got stuck in a loophole. I tried using u substitution here, u equals cosine u, or maybe I could use w equals cosine u and do another u sub, but it doesn't work that way. What you actually do here is you use this identity here, which is equals cosine squared x minus 1, if I'm not mistaken. So take a look online how to solve this integral here, and you will come up with this identity. So what we have here is a squared L over 2 pi, right? We have the bounds here, which are pi over 2 pi over 2. This is negative cosine squared, which means that this will be cosine 2x over 2 plus 1 over 2 dx. I just changed everything back to x, right? Because it doesn't matter. We're just placeholder variables here, right? Cool. So now we can integrate this fairly easily, I hope. A squared L, we got 2 pi. We got antiderivative here, so I can go like this, boom. I have 1 over 2 times integral of cosine is sine 2x. And over here we actually have divided by another 2 because there's a 2 in here. We do like chain ruler or u sub or whatever it is. Then we got plus, and then here we have 1 over 2, which is antiderivative of that is x over 2, right? Now we have pi over 2, pi over 2, and we can solve this out. Remember, all of this equals 1, so we got 1 is equal to a squared L 2 pi, boom. Now we can take this top bound, plug it in everywhere we see x, so I have 1 over 4 times sine of pi over 2, which gives me pi right here, right? Because the 2 cancels with the other 2. So we got plus here, I think we got pi over 2, so we got plus pi over 4, right? Boom, minus, and now I subtract and plug this everywhere in the x. So I have 1 over 4 times sine of negative pi in this case, negative pi. Okay, then we got a plus over here, we got a pi over 2, but actually there's a negative over here because it's negative pi over, and it's negative pi over 4. Cool. Close that, close this, and we got 1 equals a squared L over 2 pi. Okay, boom. Sine of pi, let me actually peep what sine of pi is. I think it's 0. Sine pi equals 0. So sine of pi equals 0. This entire thing equals 0. Let's do sine of negative pi should also equal 0. Okay, so this entire thing also equals 0. That means what we have left in the brackets is pi over 4 minus pi over 4, so plus pi on 4, right? This equals a squared L over 2 pi. Inside here we got pi over 4 plus pi over 4, which should equal pi over 2. Nice. So now we can cancel some stuff. We got a pi here, cancels with this pi. These two 2's combine, which gives us a 4. We got a squared L over 4. Nice. So now we have this final equation, a squared L over 4. If I multiply this 4 and this L, I get a squared is equal to 4 over L. Okay. Square root both sides, so we get square root of this is equal to 2 over root L. Right. Interesting. So let me check my solutions, see if this is right. And we actually do get the right answer. So here is the right answer. It matches exactly with this one. So this is good. This is for part A. Now part B was find the probability of finding the particle between x equals 0 and x equals L over 8, right? So how we determine this is we again take an integral. Now we have x equals 0, x equals L over 8, because we're just looking for the probability between those spots. And if we do this integral here, right here, what we will get is a percentage of finding the particle between these two bounds over here. This is the same thing as the normalization condition, except the normalization condition, we go from negative infinity to positive infinity, and here we get 1, which is 100%, which means we look across the entire x-axis, and we have a 100% chance of finding the particle somewhere there. The particle must be somewhere on the x-axis, right? Because it exists. So now we have the specific bounds which we are looking for. And what we can do is actually rewrite this as L over 8 over here. Now we have A, which we know is 2 over root L. So we have 2 root L over here. Now we have cosine 2 pi x over L. All of this close, absolute value bracket squared dx. How do we solve this? Let's distribute all of this stuff. So we have L over 8. Remember, this now does not equal 1. We are actually looking for what this equals. We have 0 here, 0 here. The square applies here, and we get a 4, and we get an L over here. Now we get a cosine squared 2 pi x over L. Cool, now we got a dx. All right, we can simplify this by pulling out the 4 over L because it is a constant. We got L over 8. We got a 0 here. Now we have another cosine squared identity. So what I'll do here is actually just use that cosine 2x is equal to 2 cosine squared x minus 1. Is that the identity we used before? Yes. And wherever I see x, I'm just going to replace it with 2 pi x over L. Just because I, don't want to do the u substitution again. If I do that, I don't have to change these values over here. Or maybe we could do the u sub. Let's see. If we get the wrong answer, then we'll do the u sub. So what I get here is cosine of 4 pi x on L. And this is over 2. And here we get a plus 1 over 2 dx. So you see what I did? I'm basically solving for this, right? Cosine squared x is equal to cosine 2x. Here we get a plus 1, and here we get 2, right? Because I have this original 2, which I have to divide on this side in order to isolate for cosine squared. This cosine squared matches this cosine squared. So I can replace this whole thing by what I see on this side. So I have cosine 2x, right? Inside here, I plug in this. So we have this 2, which multiplies by this 2, which gives me a 4. I have this divided by 2, which I have here. And then I have a plus 1, which I divide by 2, so I could split the fraction, or split this composite fraction up into 2 different parts so I can integrate a bit easier. Now I think I'm ready to solve. So I have 4 over L. Let's just, you know what? We don't need to simplify. We could literally just integrate at this stage. So I have cosine of some composite thing over here. So I know integral of cosine is sine. And then here I can put 4 pi x over L, but I need to divide by this entire thing inside. So here I'm already dividing by this 2, so this 2 stays, and when I divide by this thing, I get L over 4 pi, right? The reason I'm doing this is because, take a look at this, right? This is how I kind of do this in my head. If I do this, and I take a derivative with respect to x of this whole thing, right? I have derivative of sine 4 pi x over L. Then I have 2L over 4 pi. Actually, maybe I shouldn't divide like that. Maybe I should actually do 4 pi over L. I think that's the correct way of doing it. Because take a look at this. If I take a derivative of this, what happens is I know derivative of sine is cosine. So I put a cosine here, 4 pi x over L, right? And everything here at the bottom stays the same, 4 pi over L. But since I'm doing something like a composite function here, I have to use the chain rule, and then here I multiply by this extra thing on the inside, 4 pi over L. Now since I have this, check it out, I have one factor here, this cancels. Then I get cosine 4 pi x at the top and 2. Which is exactly what we had here, cosine 4 pi x over 2. So if I take a derivative of the antiderivative, I should get back the original function. This is how kind of I double check integrals in my head. If it didn't make sense, don't worry about it. You don't really have to do too many integrals in this class. You really just got to know the theory of like quantum mechanics, like what's happening, why are you even taking an integral here. If you get stuck at the integration part, you would just ask for some help. And most of the time it should be okay. So now I have this. I did confirm that this was incorrect at the bottom. This should be actually divided by just this little prefactor, like that, boom. And I'm also not done here. I have a plus 1/2, which should equal plus x over 2 if I take an antiderivative. Or if I take a derivative of this x just becomes 1, and then I have back my original function, which is 1 over 2. All right, so let me erase this, simplify it a little bit. Boom. Now I can put my bounds, 0 at the bottom, L over 8. Now I can take the integral by just plugging this stuff in over here. So I have big brackets, interior brackets. I can take this L over 8 and plug it in over here. So I have sine of 4 pi L over L times 8. We could see here that this cancels with this. 4 divided by 4 is 1. 8 divided by 4 is 2. So we could simplify like that. And here we have 2 times that is 8 pi over L. Nice. Now here we have plus L over 2 times 8 is 16. Close this, subtract. On the other side, we do the same thing, so we plug in 0. So this should be easier. We have sine of 0 because everything here is being canceled. I'm going to put a big bracket here. We got 8 pi over L. And then I think sine of 0 is 0. Let me actually double check that because I always forget things like this. Sine 0 is 0. So actually this whole thing here goes to 0. So I don't even need to worry about it too much. And then plus x over 2, you plug in the x equals 0 there. So you get plus 0. So this whole second side actually equals 0. So let's simplify this again. 4 over L. Here I get sine of, what I have left there is just pi over 2. Is this correct? I think it is. 8 pi L plus L over 16. Okay, so now I kind of want to simplify things. And how do I simplify things? Well, let's check what sine of pi over 2 is. Should be 1, right? Sine pi on 2. Ooh, this is actually 0. Interesting. So sine of pi over 2 is 0. So this whole thing is 0. That means this whole thing is 0. That means we just have this left. So we have 4 over L. And this is being multiplied by L over 16. Does this even make sense? We have an L here at the top, which cancels with this L at the bottom, which looks good. Now we have 4 on 16, which is, we divide by 4 by 4, we get 1. We divide 16 by 4, we get 4. So we get 0.25, or this is 25%. Let me check my solution manual here. Ooh, not correct. The answer is 40.9%. Let me see what I did wrong here. Sine of pi over 2. Bruh, okay, this is what happened. I Google searched sine pi on 2, and this told me it was 0, but what it actually did was sine of pi on 2, and this gives you 0 over 2, which gives you 0. So I said this whole thing here equals 0, which is incorrect. So always check your calculations. Let's erase this, erase this. All of this is incorrect here. Incorrect, incorrect. Erase this, this is incorrect. Erase this. I said all of this was 0, but what we actually got was sine of, let me check again, sine of pi over 2. This should be 1, bro. I knew it was 1, man. I knew I was tripping out here. So this entire thing here actually equals 1. Okay, hopefully this actually solves the problem correctly. We get 4 here, we get an L here. We get 1 over this is equal to all of this flipped, so L 8 pi. Then we get an L 16 over here. How do we combine these fractions? Okay. Actually, can we factor out an L? If we factor out this L here and this L here, these L's can cancel with this L, which gives us something a bit simpler to work with, I think. So we have 4 here. Then we get 1 over 8 pi plus 1 over 16. Okay, let's bring everything to common denominator here. So we get pull out my calculator actually. I guess you can plug all this in your calculator, but we got 8 times 16, which equals 128. So this equals 4. We get 16 over here over 128 pi. Does that make sense? Multiply 16 on the top and bottom. Basically what I'm doing here is I'm doing times 16 here, times 16 here, right? That gives me this 16 on the top. 8 times 16, 128 times pi is 128 pi. Plus, now I multiply by 8 pi here, times 8 pi, times 8 pi. Now here I get 128 pi again. So what that gives me is 4. Here I have on the top 16 plus 8 pi over 128 pi. Okay, I guess we have to use a calculator anyway. I don't know why I did all that. 8 times pi equals 25.13. I will do plus 16 equals 41 point blah 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 divided by 128. Actually, let me erase. Damn. Divided by brackets 128 times pi, close bracket, equals 0.10. Multiply that by 4 equals 0.409, and then some other numbers there, which actually equals 40.9%, which is, as you guys saw before in the solution manual, the correct answer. Boom. So I hope this problem was helpful. Let's take a look at it overall. We have a wave function here, and you know what it looks like. Then we are asked for the normalization constant A and the probability of finding the particle between this region here. First thing I did was plot. I saw that the function looked like this. Then I used the normalization condition, which is over here, to break apart my integral, solve for an integral. All of this equation equals 1, and then boom, 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 after some calculation, after some spooky stuff, I can isolate for A, which gives me this. Now I have a wave function which I can actually replace the A for because I've calculated it. Now if I want to find the probability between two bounds, I have the first bound here, I have the second bound here. I put the bounds here, I integrate the absolute value squared of the wave function. Now we have the entire wave function. Cool. We can go through the same kind of calculation. Make sure your integration and your calculations and your calculator is set to radians and all that, and you find this. So I hope this was helpful. Please let me know if you have any questions in the comments down below. Try these problems out on your own. Thank you for watching. As always, peace out, guys.